Hello everyone, welcome to our YouTube channel Electronics Maddie. In this video, we're going to talk about maximum power transfer theorem, the theory behind maximum power transfer theorem, and few of the solved examples with respect to maximum power transfer theorem. So let's get started. Maximum power transfer theorem. So the name itself gives you an indication that it is something related to maximum power transfer, isn't it? So let's look at the statement. The statement is pretty simple. So maximum power transfer theorem states that maximum power is delivered from the source to the load when the load resistance is equal to the source resistance. What does that mean? If you have a network or a circuit, maximum power is said to be transferred from the source V to the load if the load resistance RL is equal to the source resistance RS. So how do we validate this particular statement? We will be proving it that when RL is equal to RS, maximum power is said to be transferred. So let's look at the proof. From this particular circuit, I is equal to V by RS plus RL because of Ohm's law, that is V by R. RS and RL are connected in series, so I'm adding them up. So power delivered to the load resistor RL is nothing but, in general, by Ohm's law, we have P is equal to I square R. I have substituted the value of RL, I have substituted the value of I to be V by RS plus RL over here. So when can we say maximum power is said to be transferred? That is equating the slope to zero, because that is the point at which maximum change has occurred. So dp by drl is equal to 0. So differentiating this, I've substituted the value of p over here. Whatever is there, I've substituted it. Next step is to differentiate it. Differentiate p with respect to rl. You will be getting this particular equation. Now I'll equate it to 0 because of this condition. You'll denominator term vanishes off, you'll be left out with the numerator term, and v square also vanishes off because it is equated to 0. You'll only be having this particular term. So simplifying this quadratic equation, you will be arriving at a point called rs is equal to rl is equal to rs. So this clearly states that maximum power is delivered from the source to the load when the load resistance is equal to source resistance. So we have understood that the statement is valid, but why is it actually stated in this way? Like, why is this statement all like required in real life application? If you ask me, with respect to real life application, our intention is always to transfer maximum power from one point to another for any circuit for that matter. So that can be done if you have an equivalent representation. This is nothing but a Thevenin's equivalent circuit, that is V and RS connected. So whenever you have a Thevenin's equivalent circuit, a simplified version of the circuit, you will be determining the maximum power by finding the value of RL equal to RS. That can be done if there are a lot of resistances. So it's very difficult to identify which is the source resistance, or there are a lot of other resistance in between. Then you cannot have a justification for the maximum power transfer to be taking place. So any network for that matter, the intention will be maximum power should be transferred, and these are especially used in amplifier circuits, amplification process from one network to another. It's extremely useful in those places. So how do we solve any problem with respect to maximum power transfer theorem? That will be a big question, isn't it? So let's look at the steps that are involved in order to solve maximum power transfer theorem. For this, you need to know how to solve using Thevenin's theorem. So you'll be having the steps to be same up to the point where you will write the Thevenin's equivalent circuit. In case you have missed out the video with respect to Thevenin's theorem, please do watch it. It will be included in the description. So first step is to remove the variable load resistor. If you are given a network and has to find the maximum power with respect to the load resistor RL, you'll first remove the terminal. Second step is you'll be finding the voltage across that point, that is VTH, across the point that is removed. That is with respect to AB, you will be naming it as AB and you'll be finding VTH. Third step is find the value of RTH from the same terminals and replace voltage and current sources by internal resistances. So it's pretty clear from our previous videos that voltage sources will be represented as short circuit and current sources will be represented as open circuit because of the internal resistances. The internal resistance ideally for a voltage source is very less, that is equal to 0. That's why we'll be representing it by short circuit. So step 4 is to find the resistance RL for maximum power transfer, that is nothing but equal to RTH that we have found out previously. This is a very important step. The RL value will be decided based on the value that we are finding it out with respect to RTH. So once this is done, our next step is to find the point at which maximum power transfer takes place. That is Pmax is equal to, we will be substituting and simplifying. This will be our final expression, that is V square TH whole divided by 4 times RTH. So any question with respect to maximum power transfer, if they are asking us to find the maximum power transfer, so you have to substitute VTH square by 4 times RTH. That means you need the value of VTH and you need the value of RTH. So you'll be finding it out using these steps. So VTH is nothing but Thevenin's voltage and RTH is nothing but Thevenin's resistance. So once these steps are clear, we will be starting off with three problems. Like first up, we'll be looking at a simple problem. So let's start off with the problem. This is the circuit representation of a Thevenin's equivalent circuit with a load resistor RL. So let's start off with our first problem. So example one, they've given us a network and they've asked us to find the value of resistance RL for maximum power transfer to take place. So how do we approach? They've not given the value of RL. Usually that is how the circuit will be. What should be the value of RL for maximum power transfer to be taking place? So in that way also you can analyze the circuit. So first up is to calculate the value of ETH. For that we'll be opening the terminals with respect to RL and we'll be having a network in this particular fashion. So once you're arriving at this particular, be very careful while indicating the directions of the currents and having a common convention. I have represented when the current entering as positive and when it is leaving I have entered it as negative. So apply KVL to the mesh, that is this particular mesh. You only have one mesh over here, the second one is open circuit, so there will be no current flowing through this path, only the current will be flowing through this path. So with respect to this path, you have plus 3 because the current is entering from minus to plus, so plus 3 volt is directly there. Now from plus to negative it will go at negative terminal, so minus 2 times I, again minus 2 times I because the current is flowing in this direction. Now we also have another voltage source, that is plus minus 6 volt is the point where the current is living. You will be writing minus 6 and equating into 0. So it is equated to 0 because algebraic sum of EMFs in a closed loop is equal to 0 according to the statement of KVL, Kirchhoff's voltage law. So we'll be finding out the value of I. So the reason why we have found out the value of I is to find the value of VTH. So how will we be able to find the value of VTH? So writing VTH equation, how can we arrive at this point? So with respect to VTH, we will be considering this particular portion and write the equation corresponding to our convention. So 6 volt because we are considering it from this point, like from negative we are considering, and it will be from minus to plus, so 6 volt is written. Again you will have plus 2 times I because I is the current flowing, and it's from minus you'll be considering to plus. So again you have plus to minus, that is with respect to minus VTH you'll be writing minus VTH. Again from plus to minus it will be minus 10 volt, and that is equated to 0. So now we'll be substituting the value of I in the VTH expression and find the value of VTH. That will be equal to minus 5.5 volt. So negative indicates that the convention that we have considered, that is plus minus, is not correct. It is supposed to be in the opposite direction, that is B has higher potential than compared to B, yes, compared to A. So 5.5 volt, terminal B is positive with respect to terminal A. You can write it in this way as well. So once this is done, our next step is to calculate the value of RTH. How do we do that? We'll replace voltage sources by short circuit. If there is a current source in the previous, like with respect to the network that is given, then we will be open circuiting it. So just a note, if you are not following these concepts, please do refer to our Thevenin's theorem old problems that are solved. It will give you a clear explanation of each and every step that is there. So with respect to this, you will be finding the value of RTH. How do you do that? 2 and 2 ohm are connected in parallel. The effective resistance will be 1 ohm, and 1 ohm and 2 ohm are connected in series. The effective resistance will be 3 ohm. So once that is done, you will be finding the value of RL. For RL, the value is equated to the value of RTH that we have found out. So RL is equal to RTH is equal to 3 ohms. Step 4 is to calculate the maximum value of power. We'll write the Thevenin's equivalent circuit. This is a very important step. You have to always follow the systematic procedure with respect to the circuit diagrams, and Thevenin's equivalent circuit should be written in order to obtain the maximum power transfer with respect to the circuit that we have given. So Pmax is equal to V square TH by 4 times RTH. So VTH is calculated as 5.5 volts previously, a whole square of it, and divided by 4 into 3 the RTH value that we have found out. So maximum maximum power transferred from the source to the load is equal to 2.52 watt when the source resistance and load resistance is equal to 3 ohms. So this is how we approach a maximum power transfer theorem problem. So once you're clear with this particular problem, we'll go into our next problem. So this looks pretty similar to the previous one. I guess you will be able to do it on your own. So the asked us to find the value of resistor RL for maximum power transfer and also calculate the maximum power. So our first step is to calculate the value of VTH. How do we do that? We'll open circuit this particular portion with respect to RL, and we'll be finding out the value of VTH. So how do we do that? How do we find the value of VTH? We'll be considering these two meshes. There are two meshes. If you carefully observe here, there is a current source between two meshes. So whenever there is a current source between two meshes, it is called as a super mesh. So the analysis with respect to super mesh is slightly different. So there is another video that is specifically done for super mesh and super node that involves few of the problems solved as well. In case you have missed out on that, you can watch that. It's given in the description. So with respect to super mesh, what we'll do is for 4 amps, we'll be writing the mesh equation for super mesh. So I2 minus I1 is equal to 4 amps. That is because I2 is in the same direction with respect to the current that is given. So both are in the same direction. So I've written I2 minus I1. If this was in the downward direction, I would have written I1 minus I2. That is equal to 4. So but in this case, it's in the opposite direction. So I've written this way. So this is equation 1, applying KVL to super mesh. So whenever it is a super mesh, KVL should be applied to the outermost manner, like in this direction. You're not supposed to consider any inner elements with respect to it. So you will be getting plus 8, because from minus to plus it's going, current I1 is moving at plus 8. Again from plus to minus, that is minus I1, you will be getting, you have written minus I1. Again from plus to minus, that is minus 5 I1. And again from this, it is with respect to I2, so minus 5 I2. And from plus to minus, again it is minus 10 volt. Minus 10 is equal to 0 according to KVL statement. So again I'll simplify this expression, and you'll be getting this as you'll be labeling this as equation 2. Solving 1 and 2, you'll be getting the value of I1 and you'll be getting the value of I2. So why do we need I1 value? This is because I1 or I2 value for that matter. This is because VTH is to be found out. VTH voltage is nothing but the voltage that is there at this point. So if you're considering this is the point, the voltage at this point and this point will be the same, isn't it? So I'll be writing the VTH equation. How do we write that? So again I've considered this portion. So this is the value, this is the point that gives you the voltage VTH. So minus to plus, plus 8 minus 1 I1 minus VTH, again plus to minus, minus VTH, that is equal to 0. Solving this, you'll be getting VTH is equal to 8 minus I1, and I1 value we know, we'll be substituting for it, and you'll be getting 10 volt. Once we have the value of VTH, we can find the value of RTH. So we'll be replacing voltage sources by short circuit and current sources by open circuit for the given problem. So I've replaced it in that manner, and I'll be getting an equivalent network in this form. Now 5 ohm and 5 ohm are connected in series, so you'll be getting 10 ohm is connected in parallel with 1 ohm. Solving this, you'll be getting 0.91 ohms. So once this is done, you'll be finding the value of RL, that is simply equated to RTH value. So please write this step. Although it looks very simple, make sure you write this step as well. So step 4 is to calculate the value of Pmax. We'll be writing Thevenin's equivalent circuit, and now we'll be finding the value of Pmax by substituting the value of by substituting our formula, that is V squared TH by 4 times RTH, that is equal to 27.47 watts. So this is the analysis that's are supposed to be done, and we'll be arriving at 27.47 watts for maximum power to be transferred from the source to the load. So once this is done, we'll go for a next problem. This looks slightly complicated, and this is really a different and a unique problem. Please stop the video at this point and try this problem on your own. If you are able to do this problem, you will be able to do any problems related to maximum power transfer theorem, any problems related to Thevenin's theorem. Trust me, you'll definitely be able to do it. So let's look into our problem. Let's start off with calculating VTH. Again, with respect to RL, we'll open circuit these two terminals with respect to RL. You'll be removing that, and you'll be having a network in this form. So looking at this, what comes to our mind is that the network looks very big. So how do we simplify this network? So if you carefully observe, 5 ohm and 10 ohm are connected in series in this fashion. Again, 9 ohm and 9 ohm and 18 ohm are connected in series. With respect to A and B, I am talking. So with respect to B, if you see 18 ohm and 9 ohm are connected end to end. So that means when they're connected to end from end to end, they're connected in series. Again, if you see from this direction, 5 ohm and 10 ohm are connected in series because they're connected in from end to end. So what we'll do, we'll be getting 15 ohms over here. Again, you'll be getting 27 ohms here. So 15 ohm 15 ohm, 15 ohm, they are connected in delta. 27 ohm, 27 ohm, 27 ohm are connected in delta. So converting delta to star, you'll be arriving at this point. So how do we get this? There is an important observation that I told with respect to solving star delta transformation problems. So please do refer to that video. It gives you a greater analysis of how to solve star delta problems. So whenever you have similar values like 15 15 and adding this, you'll be getting 15, 27 27 and adding this, you'll be getting 27. So the when you're transferring from delta to star, the effective value will be the value of each resistor. Will simply get it by dividing it by 3. That is a shortcut. So that will be helpful for solving competitive exam problems. So 15 divided by 3 is 5, 15 divided by 3 is 5, 15 divided by 3 is 5. We are writing 5 5 5 5. Again, 27 divided by 3 is 9, 27 divided by 3 is 9, 27 divided by 3 is 9. I've written it in this format. Once you have the circuit, from here on the problem looks very simple. The reason, because we'll be solving it, just have a look at it. You yourself will realize that this problem is very simple from here on. So I've written the circuit just to from our previous slide, just for you to see how it looks like. So I is calculated as, see, the voltage source is here and the current will be flowing only through this path because this path is already open circuited. So current will be flowing in this path. That means 5 ohm, 5 ohm, 20 ohm, 9 ohm and 9 ohm all are connected in series. By applying Ohm's law, that is I is equal to V by R, 100 divided by these values that are connected in series, you'll be getting the value of I. So why do we need the value of I? Because we need to find the value of VTH. How do we find the value of VTH from I? Just look at this. So I'll be applying writing the VTH equation with respect to this particular portion. So if you're considering this direction, so 100 minus 5 times I, it is living at minus 5. Again, you will be writing it as with respect to VTH, that is minus VTH. Again, with respect to 9 ohm, you will be writing it as minus, it is living at minus 9 ohm, so 9 times I. So in this way, what will be arriving at, VTH is equal to 100 minus 14 times I. So I'll be adding these two and you'll be getting this one. So once we have that, we know the value of I, will be substituting it and we'll be getting the value of VTH to be equal to 70.88 volt. I hope this step is clear. If you have any doubts with respect to it, please do feel free to reach out to me. So step 2 is to calculate the value of RTH. So how do we do that? We'll open circuit the voltage, we'll short circuit the voltage source and open circuit the current source, if any, in the circuit, and calculate the value of RTH from that point. That is nothing but the effective value of resistance of the entire circuit. So looking at this circuit, it is very clear that I'll be adding these three, and the effective combination is written in this manner. If you carefully see with respect to the circuit that is given, 5 ohm and 9 ohm is written as it is over here, and with respect to this, 9 ohm is written as it is and 5 ohm is written as it is. 5 ohm, 20 ohm, 9 ohm are again connected in series, but the effective combination is connected in parallel. So how do you say that is they are connected in parallel? If they are connected between the same 2 points with respect to this. So once you arrive at this point, you will be able to solve it easily. I've written the circuit just for your reference in this point. So I'll be reducing this further. That is 5 ohm and 9 ohm are connected in series. I'm adding them up. 5 ohm, 20 ohm, 9 ohm are connected in series. I will again add them up. So you'll be arriving at this point. Now looking at this, all of them are connected in series. You'll be adding them up with respect to terminals AB. You'll be getting RTH as 23.92. So once this is done, step 3 is to write the value of RL, that is equal to RTH, that is 23.92 ohms. Our final step is to find the value of Pmax, that is given by write the Thevenin's equivalent circuit, and then Pmax is equal to V squared Th by 4 times Rth. Substituting for the value of Vth and Rth, we'll be getting 52.51 watt. So I hope this problem is clear. This is one of the most slightly trickiest problems with respect to the other ones that are solved in today's demo. If you have any questions, please feel free to reach out to me by typing in your questions in the comment section below. If you like this video, please do like it, share it, and subscribe to our channel for regular updates. Thanks for watching this video.